Okay, a couple things. Where's it there? This, all right, yesterday I ended with this model where we're kind of adding servers and removing servers, and then there was this kind of weird condition that I couldn't understand why it was there. And the reason I couldn't, because it was a typo. So this is the correct one. I think that I've replaced the slides. Sorry. Yeah, the one problem with the class that's immediately after lunch is like all of my blood is in my stomach and not in my brain. So that's anyway. So what was the issue? The issue was when a customer arrives, what you're checking is the queue bigger than or equal to that trigger point for adding another server, and are the number of servers that are on the floor less than the total that you actually have, because you're about to add another server. You can't add them indefinitely. You can only add them as long as until you run out. So little k is the total number that you have available. And so even if the queue hits that threshold, if we've run out of servers, then we can't add anymore. We can't something that you don't have. So just be mindful of that. That's a good question. Okay, the question is, should it be less than k or should it be less than or equal to k? So remember, little k is the total number I have available. And the thing is, I'm scheduling an event that's going to add 1 to it. So if it's less than or equal to, and I add 1, I'm going to have 1 more than I have available. So that, yeah. But that always ask that. I mean, in other words, always say, okay, should that be less than, less or equal to, so likewise on Q, should that be greater than or equal to? It depends on it depends on the rule. The rule is when you hit that capital T, we add another server if there's one that we can add. But yeah, always question. It's like when I told my son, question everything, and he said, why? Give it to me again. See it. All right. Okay. Before, well, the other thing is that, let me come back to this. We also had this model of servers with efficiencies that we did as an event graph. And the main difference between this and actually the entity servers was that in addition to having customer entities in a container to represent the queue, we have server entities in a container to represent the available servers. And so what I wanted to do is I wanted to look at the implementation of that. So in the class code, if you do a pull on that, you will you'll see the implementation that I've done. Okay. And just a couple things about, I know that some of you have been struggling with the latest computer assignment, so I want to kind of re-emphasize what I think is the optimal way to go about implementing a model like this. And that is, well, to take baby steps and test each step that you take. That's the thing. So, and and sometimes the steps, how should I say? It's like the let's see, so this is in, so just sort of starting with the customer, like in this case, we're having, we want a customer who's going to carry around their service time. They're going to, so instead of the server owning the service time, the customer is going to own it in this case. Which is right? You know, it's a modeling choice, you know, so you have both options available to you. And so here we're doing this option. So the way to do that is, so when you have a situation where you have one of these passive entities and entity itself doesn't give you everything that you need, and in this case, entity doesn't have a service time. So what we do is we subclass it and we add the whatever additional values that we want. Now the other thing is that when we just bears kind of pointing out is that the every entity sort of has a quote name, and the default name is just entity. But in this situation where we're going to have both customers and servers, when we run it in verbose mode, I want to be, if I look at something, I want to be able to tell whether it's a customer or a server. And a way to do that is by giving it the name customer. And it's in the superclass constructor. In fact, we can take a look at it. We see that the entity has in the job, and for those of you doing Python, there's a Python version that's not quite as developed as what I have here, but it's more or less complete. But so we have a zero argument constructor that uses the default name. Notice the default name is a static variable called entity. But on the other hand, if we give it a name, then it'll use that name as we'll see. So that's the other thing is that when we in this case I added a setter. You know, again, it's a choice in this whether to have a setter or not. But in either case, because the service time needs to be something which is positive, if I give it a service time that's 0 or less, then I want to immediately throw an error. In this case, an illegal argument exception. We're using one that's built into Java, as at least those who had the Java course last time. No, we can always roll our own exception if we want, and it's a fairly easy thing to do. And you want to do that only if the existing exceptions don't give you what you want. In this case, illegal argument exception is the perfect one because we've given it an illegal argument, literally. Okay, so now the second thing is in this case, the customer arrival process and extending an existing component. So this is how we implement that.
Hey, sir, are you sharing your screen?
I thought I was.
I'm only seeing you.
Okay, looks like I'm not. My apologies. You should have stopped me sooner. Okay, is that better?
Yes, thank you.
Okay, sorry. Yeah, thanks. Okay, where are we? Come on. And so keeps, all right, so just to kind of recap here. So here's our customer, and it extends entity. And again, for those in Python, there's a comparable thing going on in Python. There's code in there. So if you pull that, you can kind of try to see what the similar ones are about that. So, and those are in, there's a new file in the Python one called server efficiencies, I think it's called. And that's where I put all the classes. Okay, so implementing an event graph component, and this is the Java version. The two choices are to extend SymEntity base, which we'll do in a little bit, or to extend an existing one. And what we're doing here is we are taking the virtue of laziness and using everything that we've already implemented in the arrival process to handle all that and just adding what we need. Now, for small event graphs like this, just to roll the whole thing from start to finish, extending SimEntityBase isn't such a big deal either. So I am 100% indifferent to which you prefer. But this is how to extend a component that already, now remember the components are going to, an event graph component is going to have parameters and usually state variables. That's why we're reusing it. I mean, we're because it's or at least scheduling events that we want to utilize. So we have a zero argument constructor, and why for that? That's, I'm going to keep deferring that. But now the convention is that the in the master constructor, the first arguments are the parameters of the superclass, and the remaining ones, if any, are the parameters in the subclass. So the arrival process, and we don't have to call it the same name. We can call it any name we want. All we need to do is make sure the type is right. So here, the arrival process has an inter-arrival time generator that it needs, and our customer arrival process needs another random variable, which we'll use to generate the service times. And so we call the superclass constructor with the parameter here. And if there are more parameters, we would call whatever parameters are there. And that would ensure that the superclass is properly configured. And then we also set our the ones that we have here. Now in this particular one, all we're doing is we're adding an extra arrival event, or we're overriding the arrival event and then scheduling in the Java version, we can schedule another quote arrival event, but with a customer argument. In Python, we have to do something a little different, but for the Python folk can see what that difference is. It should be pretty obvious. So in this case, and when I get to some of the slides, I'll talk about kind of what this is about. Should we always call the superclass event? And the answer is no, not always. Sometimes we want to completely override it. And sometimes we want to override it, adding stuff, but also utilizing what's in the superclass. In this case, we want to call it because this will schedule the next arrival event for because that's already been implemented. But we want, in addition to that, to be adding this other one. So if you remember how overriding works, that kind of the event list is going, when it gets the arrival event, it basically hands it back to the object that schedules it. And when what SimEntityBase does is SimEntityBase says, in this case, I got an arrival event. Do I have a do arrival method with no arguments? That's the one that was scheduled by the superclass arrival process. And if I do, I will invoke it. Now remember how the invocation works. If I invoke an overridden method, I'll invoke it in the subclass. And if it's not there, I'll go to the superclass. So this do arrival is the one that gets implemented when the event list processes the arrival event that was scheduled in the superclass. Okay, you got that? Okay, but we also want the logic in the superclass, so that's why we call it here. Now, we don't always want that. So this isn't a hard and fast rule. It's a specific rule for this instance. Because we want what's in the superclass, we call it there, and then we instantiate our customer and then schedule arrival with a zero delay passing at the customer. Now, the thing is, okay, now this is what can make a difference between kind of banging your head on the keyboard more as opposed to less. I'm not saying I can prevent banging your head on your keyboard, I bang my head on the keyboard on a daily, if not hourly basis. But this minimizes it. Okay. And the minimization is, okay, what we have done is just kind of do this, and it looks okay. But just because code looks okay doesn't mean that it is okay. So run a test, always run a test. So here's the test. I call it test customer arrival process. The difference between a test and a run is that a test is just to confirm that it's working, and a run is the longer ones, but that doesn't really matter. You can call it whatever you want. All right, so we create our inter-arrivals, our service times, and so I instantiate it, and then I always print print the thing. Why? Because it will show me what the parameters are, and it will show me that the parameters have in fact gotten in there. Then run in verbose mode for a relatively short amount of time. Verbose mode for the schedule or the event list in the Python version shows you every event that is on the event list, as well as every event that gets scheduled. And as they get scheduled, they show this is the time, this is the event, and this is the event list. So that's how you figure out what the heck is going on. Now, in the process of this, I wanted to show you, so far, we've mostly been doing something called stop at time, and that stops after a particular amount of time. There's a second way to stop a simulation, and that's stopping on an event. And the call is stop on event in both Java and Python. The first argument is how many events I want to stop on. The second argument is the name of the event. And then in the Java version, I need to give it a signature. Now, if there's no signature, I don't put anything there. But if there is, I put the class of the argument. So this says stop after the 5th arrival with a customer as its argument. Okay, and that's a different event than the arrival event with 0 arguments. Now, in the Python version, just for those of you doing the Python, this last argument is not there. Why? This argument needs to be there in Java because of method overloading, because Java supports method overloading. In fact, in this case, we have arrival events which have 0 arguments, and we have arrival events that have customer arguments. And so if I just say, well, if I leave the customer class off, it will look for arrival events with no arguments. Now in Python, because Python doesn't support that, I can't do that in Python. So if I say, so in Python, I don't even need to tell it, even if there is an argument, in the Python one, I just need to give it the name of the event. Okay, but always do this. In fact, if there's more than one event that you're implementing, implement the events one at a time and run it in verbose mode each time to make sure that what you've implemented is doing it correctly. Just what the tendency, and believe me, I have the same tendency, is to kind of implement more things that you've tested. So my exhortation to you is to write one method, write one event, and test that. And then don't move on until you're convinced that that is actually correct. So when we run this, okay, a couple things. We want to confirm that the service time generator inter-arrival, they got there okay. Okay, there's the run method for, so when you begin, the run event is always on the event list. That's where we start. And if we have, for every component that has a run event, as you've seen, they're They're all there. Okay, so here's the run event. I'm looking, there's the arrival scheduled. Here's the arrival that's occurring, and then the arrival is scheduling an arrival with a customer in there. And in fact, I want to kind of check on this because, well, you might be wondering what these two numbers are. The first number is the creation time. That's what's used for the age. And the second one is the timestamp. So at the beginning, both the creation time and the timestamp are whenever it was created. Okay, so, and then another arrival, and then let me kind of come down. In fact, we can check with this. We see that the fifth arrival event with a customer is where the thing stopped. Okay, so, and again, I don't want you to be spending inordinate amounts of time trying to figure out why things aren't working because there were a lot of methods that were written that haven't been confirmed. Because that's just sort of crazy making. And I've seen, in the past I've seen it in some cases here as well. And just I can't encourage you more strongly not to do that. Right? One event, now one event might be, remember the run event has both the reset and the run thing. And then like in the, let's look at the, in other words, it's okay, server with efficiencies here. So this is that class, and this is a little more complicated. It has, and then first things to do is the very first thing is to put the parameters in, do the setters, getters, and constructors, and then test it. Test it to make sure that they got in there. I mean, again, what can go wrong? Well, what if, here's a real easy thing. In fact, this just happened to me this morning on another thing I was doing. I forgot to set this. So what happens if I just do that and I try to run this? Then I'm going to get null pointer exceptions everywhere. But okay, why was I getting null pointer exceptions? Let's go back to here where I'm saying, the service time generator was null. What happened? I didn't set it. Okay, so why is the service time generator null? I created it right here, and I passed it to the, just like go back to say, whenever you have a null pointer, I mean, those are the best exceptions to have. When you have a null pointer, that says you are trying to invoke a method on an object reference that was null. Okay, so now why were you trying to, why was that null? Well, go back to the, again, supposing this happened. Okay, I mean, I know what happened. I made it happen, but it's okay. Supposing I didn't. I say, well, okay, what the F? Okay, why did I think that shouldn't have been null? Well, okay, here, I instantiated it right here. All right, that's fine. Did I pass it to this object? I sure as heck did. There it is. Okay. So, all right, let's see what's going on there. And then here, this actually wouldn't even be there. And I say, oops, now all of a sudden, here it's being passed in, but isn't being set. So problem solved. And then one of the nifty things about Git that I hope you like. Okay, here's an example. I did an edit. I don't like the edit. I want to undo the edit. I want to go back to the way it was when I first started the session. So you click on a blue piece. I choose Git, revert modifications, and it's going to take me right back to where I was at the beginning. Why? Because I don't know what your experience is, but sometimes I write a bunch of code and say, boy, that's a bunch of crap. I want to go back to the way it was originally. Okay, so now and unfortunately there was a little that should have been a diamond thing anyway. Okay, so now with instantiating container state variables, as we've done here, can be a little, that's one of the little tricky things. In this case, the strategy is to instantiate them in the zero argument constructor and make sure I call this. And then this way that I know that they're always going to be instantiated. And so my strategy in initializing them is to clear them out in the reset method. And then for ones like in this case, the available servers to put the, in this case, we're going to populate the available servers with this array that we're going to pass in. And so whenever I have something like that, then the first thing you should think of is that event graph for loop, that kind of little init thing. And that's what I've done here. So in the reset method, I'm clearing both of these out. But then in the run method, okay, I'm scheduling the queue I want to keep empty, so I'm fine with that. But I want to schedule my init. And so what I'm going to do is I'm going to add them in one at a time. In fact, each time I'm adding them in, I'm going to also fire a property change to say, okay, I've added this server in, and that will. So what I should see is as the init things build up, I should be able to see those happening, and so I can make sure that okay. So because what else can go wrong? Well, maybe I'm not rescheduling my inits correctly. That's another thing that, I mean, there's so many things that can kind of go wrong. And just kind of the little thing here, the reason I'm stamping the time here on this server is because because my container is a sorted set for the servers, and the thing with entities is that the first criterion for ordering the entity is the timestamp. And so what I want to do, if I have more than one server, is I want to kind of rotate them. And what that means is that when I'm finished with the server, I want to put it back at the end rather than at the beginning. And so to do that, I'm going to stamp their time when I do the end service, as we'll see. So now when I come back to do another replication, the timestamp will be the one that I finished with before, because I'm going to use the same object. And so I'm going to restamp the time because now we're back at time 0. And then, okay, so now all of this is fairly straightforward, pretty much the same as the entity server. Just the one thing here that makes a difference is that when I'm scheduling the end service time, the end service event, I get the service time, the basic service time from the customer, and then I multiply it by the efficiency of the server. And as was pointed out yesterday, the efficiency property, less is better. So if I have if it's less than 1, then it's going to go faster. If it's greater than 1, it's going to go slower. Okay, so and then, let me see, yeah, so here at the end service, here I'm kind of passing these here like this. And so I'm stamping the time before I put it on. Why? Because that will kind of put it at the end. So a server that was previous will have a smaller timestamp, and so it'll be in front of it. That'll just kind of rotate it. Otherwise, you're kind of taking the same server. Now that's also, by the way, something which one could modify. You might say, okay, instead of that, what if we just had, well, I don't know, always had one server before the other ones. I don't do the timestamp, that's what's going to happen. Anyway, okay, so now let me show you. Now, there were some things I wanted to illustrate in showing them. There it is. Okay, so here's the run method. A lot of this is, now notice in the comments, I've commented out what, when I was, and that, I eat my own dog food here. When I was writing this, this is what I did. I mean, first I implemented the run, and then I ran it in verbose mode. And then I implemented the inits, and I added this simple property dumper, and I ran it to make sure all the inits were happening correctly. And then I added the arrival event, and then made sure that the arrivals were showing up and scheduling the start service. Then I implemented start service and made sure that that was showing up and doing the correct state transitions and scheduling the end service. And finally, I implemented the end service and verified that all of that was working. But that was the sequence. And I did all of that in verbose mode with a relatively short run, checking the event list and the property changes at every stage. And by doing that, I mean, of course, I picked up some things that I'd messed up on. But if you charge forward without doing that, then all of a sudden you get to the end, you try to run it, it doesn't work, and you go, okay, why? What did I do that caused it to do that? It could have been anything. This way, I know that whatever I just did is, if there's a problem, cause it to do that. Okay, so now I wanted to illustrate this stop on event thing. So here I'm going to say I want to run it for 100,000 service completions. And so, I'm going to run it for this many service completions, the end service event, and it has a signature of customer and server. So I give it that. And of course, I verified in verbose mode that in fact it would end at that, because if you kind of mess up on that a little bit, so for example, if I forgot one of these, it would not catch it, and it would just kind of keep charging along. It would never end. And then you have to kind of blow it up. Okay, so now I also wanted to illustrate, just as a little peek ahead when we start doing more statistical like things. This isn't so much a statistical thing, but I wanted to illustrate what was happening with the server. So the thing is here is that when we run this, with our servers running at a normal speed, the measures as we'll see, the measures are not great. And so how can we improve measures? For a system like this, there are basically only two levers that we have. We could add more servers, which is often kind of expensive. I mean, if we're talking machines can run in tens, hundreds of thousands of dollars. If we're talking about hiring another individual, again, that's even more expensive often. So, or, another one is we can make the servers go faster. So how can we make the servers go faster? Well, we could train them. We could, maybe upgrade the processes so that whatever they're doing, they can do more easily. In fact, my kind of back in my early days, when I worked in a machine shop as kind of a lowly gopher, basically, the people on the shop floor kind of knew much more about how the thing worked than the people in the front office. In fact, one of the guys once told me, he says, if you really want to screw things up, do exactly what they tell you to. But okay, so there are ways that the server can go faster, and that will basically improve the efficiency. So and this is not statistically significant, but what would happen if, say, we could just take one server and make it 10% more efficient? So change their efficiency from 1 to, say, 90%. And that's what this does. So let's. Okay, so I ran 2 replications. So here's and I was kind of printing what they are. Here's the first replication, and we see that the servers have unit. There's the thing is 1. We ran it for 100,000 serves, So now, the time is whatever the time is. In this particular case, we had 100,000 served. There were 100,018 arrivals, so there were still 18 people stuck in the system. But what we're looking at here is the average delay in the queue, 24, average time in the system, 27, average number in the queue was like 16, and the utilization was 0.9. So, but for the second replication, notice we improved the efficiency of just one of the servers from like 1 to 0.9. And we ran it for the same number. Now the random variables are different here. So it's not, if I wanted to do, well, if I wanted to do it exactly or more like this, I would reset the random seeds so that, but I didn't do that. But nevertheless, and if I'm doing multiple replications, I don't want to do that at all. But okay, so we still had 15 more arrivals than we had, but look at the measures. So the average delay in the queue went from 24 to like 5 something. And the average time in the system went from 27 to 8 something, again, difference of approximately 3 or whatever. The average number in the queue went from 16 to like 3.5, something like that. So that one little tweak, now, of course, now these numbers, I would have to do multiple replications and do confidence intervals and other kind of stuff for it to be statistically accurate. But the magnitude of the change is such that when you do that, it's going to kind of work out. So what's the point? The point is that this little tweak here, like if I'm asking the question, what would happen if we, by one way or the other, improve the server efficiencies versus maybe hiring another one? If I can put a cost to this, should I spend money on training or upgrading the processes, or versus the money it would take to hire another individual? I can make that comparison. I mean, and I may want to just hire someone else. But I have the means with which to make that decision in a more, in a more evidence-based way, let's just say, instead of the field method. Okay. Questions? All right, so now I'm ready to begin. Here. Okay, and these are the things that we've already kind of talked about, but that is these subcomponents. And now I want to talk about it in kind of a more abstract methodological way. And then I'm going to illustrate it with, well, I don't have time to do all of them, but I'll finish them up tomorrow. To remember that we had that batch arrivals problem and the question is, how can we implement it? And can we implement it in a way that reuses some work that we've already done instead of doing it all from scratch? Okay, so subcomponents. I mean, now it's, how should I say, inspired by inheritance in object-oriented design. So the event graphs are just these circles and arrows and things on a page, but conceptually, we can be, quote, just as lazy as with inheritance by reusing features. And we've already seen that with the arrival process in a number of different settings. And the thing to remember is that the subcomponent has direct access to all state variables, including those in the super component. And then now it has indirect access to parameters via setters, getters, and that's in the implementation. In the event graph itself, we could kind of just, how should I say, it's like in the event graph, we don't do set and get and all that. I mean, but it's implied. Okay, and it's similar notation as the UML diagrams. So so we can use that same little open arrow. So if we have an event graph component and an event graph subcomponent, we can illustrate it this way. Now, as we've seen, not as we've seen, but as I've talked about, there are actually several different things to happen to events that we are overriding. I mean, and these are the notations for that. So if there's just sort of a regular old event, then what that does, this is in the subcomponent. If it's got a thin line, a thin border, then it augments the event in the superclass, the supercomponent, meaning that just as we saw with the customer arrival process, it means we want the event in the supercomponent as well. And that's in 99.9% of the time we do that. That's the first thing. First thing we do is we do that super. Now, alternatively, as I alluded to, sometimes we want to completely override the superclass event, the supercomponent event, and that's indicated by a thick border. So that says, when we see a thick border, that says forget the event in the supercomponent. We're going to just use the what this one does. And then the one with the dashed is, as we've seen, in fact, we saw it in the customer arrival process. Notice it's scheduled an arrival event with a customer argument, but we didn't implement that. Why? Because we didn't need to. The only purpose of that arrival with the customer argument was to be heard by somebody else. So there was nothing to really implement. Now, normally, if we're directly invoking a method, that method had better be there. The event graphs are more forgiving in that so what happens in that case is the event list comes back to that customer arrival process with an arrival event with a customer argument. And it says, here's your event, here's your method. So look for a do arrival with a customer as its argument, but the customer arrival process doesn't have one. And so what happens? So anyway, it's kind of a design choice. So what do? Do you throw an error, or do you say no harm, no foul? And the answer, as you might guess, is no harm, no foul. If I hear an event that I don't have, then that's on you. And in this case, there's no actual harm, because the only purpose of hearing that event was for it to be heard, or of getting that event was for it to be heard by somebody else. So that can be indicated in the event graph with a dashed line. In other words, I'm scheduling an event, but it doesn't, I don't even implement it. Okay, so let's see, I have 5 minutes left, so I'll talk fast. All right, so let's look at this batch arrivals thing. So we look at our basic multiple server queue. We're kind of back to that, and then we notice that the assumption on that is customers arrive one at a time. But what we're modeling maybe is like a restaurant, and then we see that a car pulls up and 4 people get out. Okay, so that's basically an immediate arrival, but not with 1, but with 4. So how do we model that? Well, again, we're going to defer the arrivals to some other component. So, but we have service times, number of servers, our usual suspects in our basic model, and now we have our batch sizes. So this, if you remember, this was the from the homework problem. And okay, so the event graph component would look like this. So if we're doing, and nothing wrong with that, we could just, we could do the whole thing from scratch like that. But the virtue of laziness kicks in, and I'm lazy. I've already implemented the simple server, which does almost everything what I want, except it doesn't do this batch thing. So what if I took the simple server and I wrote a subcomponent? Okay, so here now I have an arrival. Now this arrival is going to totally override the arrival in the simple server, but I'm going to increase my queue by that batch size. And now I'm going to schedule my start service, but then keep scheduling the start service. So now notice that this has a thin line, which means every start service here is going to schedule the superclass start service, which in turn is going to schedule the end service, as well as remove the super component here is going to decrement both S and Q. And so if you remember from the assignment, we keep scheduling start service as long as we have a server and as long as there's somebody in the queue. And so, so here basically, now contrast the amount of work you would have to do to write this. Again, this isn't a huge amount, but to write all of this from scratch versus just writing this. So and the models are exactly equivalent. The models will behave exactly the same. Yes, question.
Why do you need to check between greater than 0? You haven't arrived at
Oh. Okay, yeah, great question. Yeah, the question is why is this additional? Well, you understand why it's here, right? But okay, why is it here? Now okay, where is that from? In running some implementations, I was using things like a binomial distribution for the batch size or a Poisson distribution for the batch size. And what is the issue if I use those for the batch size? Yeah, so both binomial and Poisson can generate values of 0. So what if I have an arrival with 0? I mean, so it was just kind of a weird thing. So that's just, so you're right. If I have a sane batch arrival process, then batch arrival distribution, then it doesn't have to be there. But that was there just because it's like I thought, I was again lazy because with Poisson I just need to give it a mean instead of any other stuff. I ran it and I was getting these weird errors. Why? Because I was getting batch sizes of 0. So that was that. But and listener, the usual thing with this. So the point is laziness. Laziness is a virtue. Okay. See you tomorrow.